Covalent bonds are going to be bonds where electrons are shared between atoms. And most of the time, these bonds actually occur between nonmetals. So nonmetals generally have higher electronegativities, which means that they are not going to want to lose their electrons similar to metals will. So these atoms will end up sharing with each other. This will create a distinct, discrete unit like water. If you were to zoom in on water, you would see that there are individual water molecules making up a drop of water. Versus if you were to zoom in on salt, it would just be a ratio of 1 sodium to 1 chlorine. And so these are what we call these molecules when they form. And that's because of this discrete unit that they are creating. So when you have covalent bonds, you're going to first start by talking about the Lewis structure of the atom. So if we were to go ahead and look here at hydrogen, and we were to go ahead and look here at oxygen, we would see that hydrogen has 1 valence electron, and it needs a 2nd valence electron because it only has 1 shell. Oxygen, on the other hand, has 6 valence electrons. It needs 2 more valence electrons to be a complete shell. So what's going to happen is these 2 atoms, and remember there's never just one of each, there's always a large quantity of each, are going to combine to complete the octet rule for both atoms without either one losing their electrons. So again, because of the fact that there are never just 1 or 2, there's a large quantity, they are going to combine in a way that will allow them to complete the octet rule. So what's going to happen is there's going to be this hydrogen and this oxygen. They're going to kind of saddle up next to each other. Same thing with the hydrogen and the oxygen. And that way they'll put themselves in close proximity for allowing them to share their electrons. And this is going to result in this. So here's 1 electron from hydrogen and 1 electron from oxygen. And here's 1 electron from hydrogen and 1 electron from oxygen. And so they are actually going to share this pair of electrons. And this oxygen and hydrogen are going to share that. Now remember, hydrogen only needs 2 electrons because it only has 1 outer shell. So that's why hydrogen doesn't need to share more than that. And so if we count this, hydrogen needs 2. So 1, 2 for that hydrogen, good to go. We count this hydrogen needs 2, 1, 2, good to go. Oxygen needs 8, 2, 4, 6, 8. And as you can see, oxygen completes its octet rule and hydrogen completes its, I guess technically not octet rule, but its full shell. So these particular electrons here are called lone pairs. Lone pairs of electrons. And these electrons here are called shared pairs. And we end up rewriting this like this to say H, and we use a line to denote a shared pair, OH. And then we always draw the electrons that are lone pairs. Now, if we look at this oxygen, what you will find is if you were to do the math on the bonds, which is the electronegativity, oxygen is 3.5, hydrogen each is 2.1. You would see that oxygen is significantly more electronegative than hydrogen, which means that even though they're sharing these electrons, you could almost consider this being more like a cloud, a thick cloud of electrons around hydrogen, and a thin cloud of electrons around oxygen. Because the truth is that electrons are way more likely to be with oxygen than they are with hydrogen. So this is what we like to refer to as a polar atom. A polar atom is going to have a side of it that is more electronegative, meaning that it's going to technically have this side that makes it negative, and this side will be more positive. Just saying that the electrons are going to side more with oxygen. Now, we all know that this is water, but if we were going to name this using the rules for naming covalent bonds, this would actually be called dihydrogen oxide, or it could be called dihydrogen monoxide. Now, we never call it dihydrogen monoxide. It sounds a lot more ominous. We just call it water. But this di stands for 2, and mono stands for 1. So this is telling you that you have 2 hydrogens and 1 oxygen in this molecule. And again, this would be a polar molecule, meaning that it has a more negative side versus a positive side. It's not completely, the charges aren't completely spread apart evenly. So if we moved along on this, and let's say now we want to talk about an atom that is nonpolar. So let's look here at fluorine. So let's say we have fluorine here, and fluorine has 7 valence electrons. And so what's going to happen is these 2 fluorines are going to share 1 valence electron each, and it's going to look like this. And what you're going to get is this fluorine, if we count up our electrons, is going to have 2, 4, 6, 8. And this fluorine is going to have 2, 4, 6, 8. And that satisfies the octet rule. So we've got our fluorines, and they've got their electrons. Remember, this is called a lone pair. All of these are lone pairs. This is these are all lone pairs, and then this is your shared pair. If we rewrite that, it's going to look like this. And we write our lone pairs. So now if we're looking at polar versus nonpolar, you will see that this fluorine has a 4.0 electronegativity, and this fluorine has a 4.0 electronegativity. So because of the fact that they are the same electronegativity on each side, the electrons are there's not going to be they're just going to have a cloud of electrons surrounding both fluorines. One of them is not going to be more concentrated electrons than the other one because of the fact that they have the same electronegativity. There's no reason for the electrons to side with one versus the other. So this is what we call a non-polar compound. This is also called a diatomic compound because it has 2 of the same elements in it. We could name this one difluoride if we wanted to. We also would call this F2. That would be the molecular formula of fluorine would be F2. So we have the name right here, difluoride and F2, and it is a diatomic compound. Now, if we were to go ahead and look at another compound and look at the rules that you were given on your notes. So let's go ahead and look at CO2, which is carbon dioxide. And so obviously we're starting with a few easy ones that you guys have all been a part of so far. So we don't really need to, start with ones you haven't heard of. So if we're looking at carbon dioxide, we know that carbon has 4 valence electrons, and oxygen here has 6 valence electrons. Sorry, I added an extra one. And oxygen has 6. So if you're looking at the rules that I added to Google Class, to your notes for bonding, so by looking at the rules, the first thing said would be to determine how many of each element you have and what their Lewis structures are. So we've already done that. We've got 1 carbon and we've got 2 oxygen. We also want to go ahead and count the number of valence electrons that we have total. So 1, 2, 3, 4, and plus 6 is 10, plus 6 is 16. So we have 16 valence electrons to work with in this particular compound. So now I'm going to go ahead and use a pencil because sometimes when you're drawing these compounds, you may actually not draw them right the first time, and I would just like to be able to erase if I need to. So the rules are hydrogen can never be in the middle because hydrogen can only make one pair. Carbon is always in the middle if it is present, and the most electronegative atoms are on the outside. And just to let you know, this electronegativity is 2 and this electronegativity are each 3.5. So in general, if it's more electronegative, it's going to be on the outside of the element. So if we go ahead and draw this, we'll start with carbon, and oxygen is obviously going to be here, and if carbon is in the middle, it's generally going to be the central atom. So most of the time what you're going to do is you're going to take carbon, put it in the middle, and you're going to start adding things all around it. And the reason why is because carbon has to make 4 bonds to fill the octet rule, versus oxygen only needs to make 2 on each of these to fill the octet rule. So we're going to load oxygen up here, and then we're going to start filling in our electrons. So we know that it's 1, 2, 3, 4. So that will give us carbon having 4. And then, so we have 16, so we still have 12. We could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if we did it how we did fluorine and water, this isn't going to work because we have put 20 valence electrons. We do not have 20 valence electrons available. So what you have to do when you start exceeding your number of electrons is you have to start making double bonds. And the atoms can actually share more than one shared pair. They can share up to 3 shared pairs. So what we'll do is we'll take these electrons and we'll move them in here. And that will now give us a double bond right there. So at this point, so if I erase this guy, and I have 2, 4, 6, 8, 10, 12, 14, 16, 18. So I still have too many. And so what I'm going to do is I'm going to take this guy and put a double bond there. And you always move it from carbon because carbon is the least electronegative, that the electrons near carbon would like to be more near oxygen. So carbon, you'll generally make double and triple bonds. It's just a common thing with carbon. So let's go ahead and count our electrons. We've got, and we can get rid of this now because if we look, let's count and see what we have. Oxygen has 2, 4, 6, 8, so this oxygen is happy. Carbon has 2, 4, 6, 8, so carbon is happy. And oxygen has 2, 4, 6, 8, so it's happy. Now let's count the total number. We have 2, 4, 6, 8, 10, 12, 14, 16. So that is how many we needed. So we actually have a double, and I'll switch to that pen for you. We actually have a double bond here, and we have a double bond here. And we're going to rewrite this as C, O, O. And so in this case, we see that carbon has 2, 4, 6, 8. That's for carbon. The oxygen has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8, which gives everybody filling the octet rule. So this is going to be written 1 carbon, 2 oxygens. We have double bonds here. Double bonds are even stronger than single bonds. And this would actually be carbon dioxide. Or you could also say monocarbon dioxide, which generally we don't actually do. We generally, if we have one of them, we just leave it as that's the name.